Okay, I thought I'd show one more type, at least how I do it. So this is for a bandpass filter. And so I have my bandpass filter steps. The first step is the same as all of them. You change your frequencies, your hertz to radians. And then step 2, the backward transformation. So for bandpass, capital omega P is 1 and capital omega S is, okay, so this is a little bit more complicated than the other one. Okay, so I already did my converting my frequencies from hertz to radians here. So you just multiply all of these by 2 pi. Okay, so I saw on the previous page that the omega P was 1. So we have to find omega S, which is probably the first part, yeah. Find omega S, the order, and then the A's, epsilon, and omega C. Okay, so this is all just like stuff you can do on your calculator, because now we've just calculated omega 1 through omega 4. So just do these on your calculator and see what you get. Okay, so these are the values I got, and then omega S is the smaller. You take the absolute value of each of those, and then omega S is the minimum of those two. So omega S would just be the 2.3589. And then the order. So I think this is the same formula we used before. It is. This second one is. And since omega P was just 1, that's why the denominator is just the 2 log omega S. So again, the A sub S and A sub P are given in the problem. So A sub S is 3, A sub P is 0.9. And then our omega sub S we just found. So you want to evaluate everything in brackets there. And I got 0.8528, and you just always go up to the next integer. So no, that would be 1. So we just have order 1. And then we have to calculate the new A's, and it depends on whether the excess is assigned to stop band or pass band. And here it's pass band. So then we look at those formulas. So we'll change our A sub P, which means our A sub S will stay the same. And A sub S was 3, so our A sub S1 will still be 3. Okay, and so for A sub S, plug in 3 for that. The omega sub S was 2.3589. And our n is just 1, so you want to square that in the denominator, add 1. Okay, so do all of that on your calculator. You should get 0.7146. And then that's a P. So A sub P1, I know it's small here, but you can always look in your own book. We're just using that value. So 10 to the, it will end up being 0.07146 minus 1. Take the square root of that. We get 0.4229. And then we can find omega C1. So it's going to be 1 over, it's going to just end up being 1 over this epsilon sub P1 because our n is 1. So you're just raising it to the first power. So you just want to do 1 over the answer you just got. And it's 2.3645. I think that's part A. Yeah, so we found omega sub S, we found N, we found the new A's, and the epsilon and the capital omega. I'm just going to check and make sure those are right. So here's the answers from the back: 2.3589, 13.7146, 0.7146, 2.3589, 0.4229, 2.3645. Okay, good. All of that is good. Okay, and then part B says find the poles and the zeros of the normalized. Well, if it's order 1, then it's like a straight line, so it has to cross the horizontal axis, and to normalize it, it's just the pole is at s equals -1. And then there's 1, 0 at s equals infinity. And there you see that. Okay, part C, find the transfer function of the frequency transformed bandpass filter. So the next part talks about the normalized, not the transformed. So for the frequency transformation, they give this formula here, but well, these two formulas actually, but before they gave these 10 steps, it was kind of in the introduction for this section, they gave the shortcut. So I have it on page 1. And they say we just make this substitution. So the normalized one, since the only root is s equals -1, the only factor is s plus 1, but then we're going to replace the capital S with this to do the transformation. Okay, but one other thing that we have to do is this step 7, which says multiply the poles and zeros of the normalized low pass filter from step 5 by omega c. So before I make that transformation, I'm supposed to multiply this s by omega c, which was 2.3645. Okay, so remember, if there's a pole at s equals -1, the factor in the denominator is s plus 1, and it was just, the n was just 1. So our transfer function of capital S was just 1 over capital S plus 1. But we want to solve for capital S and then plug that in and transform it into a function of little s. So really what we're going to do is capital S equals s squared plus omega 2 omega 3 over 2.3645 omega 3 minus omega 2 times s. So then the frequency transformed, well, this function evaluated at s equals that is going to give us 1 over, so that whole expression plus 1. And what I would do is get everything in the denominator to just be one fraction. And now I'm just going to write it as h of little s. Will just be that 2.3645 omega 3 minus omega 2s. The first numerator stays the same. But the 1, it was like it was 1 over 1, so you multiply top and bottom by the LCD. And then you just can invert and multiply. And then we found omega 2 and omega 3 way at the beginning. That's when we changed from hertz to radians. And so just use your values of omega-2 and omega-3, plug those in to get all those constants. I get right here, when I multiply everything out, all I did was rearrange and put the S term in the middle and the constant at the end. And I think, so part C, find that transfer function, find the Q values and omega naught values. Okay, so everything we're dealing with, the constant is omega naught squared, so you just take the square root to get omega naught, and the coefficient of S is omega naught over Q. And then, so once we know omega naught, then we can solve for Q. So just take the square root of the constant. And I get about 17,017. And so then if omega naught over Q is equal to that number, I'm going to multiply by Q and divide by that 15,000 to solve for Q. And then plug in for omega naught, 1.134. Okay, and then I'll go check my answer to this. Okay, so there's the transfer function, and I just rounded. You could have kept going, get that. So there, my transfer function looks good. There's my Q, there's my omega. Okay, so that looks good. So good for part C. Okay, so part D. Find the normalized component values for the Sallen-Key circuit for each second order section. Now, I do have Sallen-Key circuit note cards that I had up maybe in another video, but they are for low pass filters. Like this one I remembered to put right on here. It's a low pass filter. The other one, I don't think I put that in the title, but I look at the transfer function and the numerator is just a constant, so I know it's also a low pass filter. So those don't work for bandpass filter. So I need my Sallen-Key note card for a bandpass filter. And it tells me what I need for the normalized part. So R1, R2, R3, RB, they're all 1. Okay, and let's see what else we have to figure out. Okay, so K, there's a K value that the R sub little a and R sub little b are in terms of. And so I was wondering, why do we need those? It was a gain adjustment. It's explained on 1140 to 1141 of the PDF, which I think is 1123 and 1124 of the hardcover. But so this, I need this to find K. So 4 minus square root of 2 over Q. And our Q is what we just found up there. And I get 2.7529. And then let's see what else. The C1 and C2 are both equal to the square root of 2, which is about 1.414. R sub A is 3 minus root 2 over K. Root 2 over Q. And notice that's just 1 less than K, because K was 4 minus root 2 over Q, so it would be 1.7529. And then what else? The R sub little a and R sub little b. So R sub little a is K over 4 minus K. And just plug in that value of K. I get 2.2076. And R sub little B was K over 2K minus 4. And again, we have our value of K, so just plug that in. So 1.8281. Okay, so this should be what we need for part D. So I'll just go check my answers. So yeah, R2, R3, they don't even list in R1. R2, R3, they're 1, RB is 1, and then there's the RA, 1.7529. Yep. C1 and C2 are 1.414. Yeah. RA 2.2076. Yep. And R sub B 1.8281. Yeah. Okay. And then the last part is just applying magnitude and frequency scaling. And as before, R new is Km times R old. So we're just multiplying by 1,000. So all of the R's go to kiloohms instead of ohms. But the C's, we have to do the transformation, but it's the C values are the same. So C1 equals C2 equals 1.414 farads over Km times Kf, and Km is 1,000. And Kf, that is omega naught, which was 17,017. And you can just do that on your calculator. And I get 8.3107 times 10 to the negative 8. And I don't know which way you want to move it. This behind the 3 would give you nanofarads. Or you can move it back and change it to microfarads. I'm not sure what they do. We'll see. Okay, so notice just the R's, all they did was change the ohms to kiloohms. 80, they did nanofarads, so 83.1 nanofarads. All right, that's what I got.